Underfitting and overfitting. Overfitting is the production of an analysis that corresponds too closely or too exactly to a particular set of data. Therefore, it may fail to generalize well to the population. So let's say, for example, you are studying for an examination, you're taking a practice test, and let's say you've taken the same practice test 20 times. You learn the answers, and you get a perfect score on that practice examination. But when you take the real examination, you underperform. Why'd you underperform? Because when you were studying, you learned the examination, you learned the answers, you learned the order of the answers, you learned what the structure of the answers look like, but you didn't necessarily understand the material. So that's generally what overfitting is. You learn the structure of the data, but not the actual answers. Underfitting occurs when a statistical model cannot adequately capture the underlying structure of the data. So let's say, for example, you have a model and you're trying to figure out a nonlinear relationship. Well, if you're using a linear regression to understand a nonlinear relationship, the model may not have strong performance and it will underfit the model. So one of the ways you might want to deal with that is by changing the model that you're using, or perhaps adding more features, or make the model a little bit more complex. Train, test, split. Use a training set to fit a model with examples, and the purpose of a test set is to determine the quality of the model on unseen data. Performance. So a high bias model has poor performance on a training set. A high variance model has poor performance on a test set. And basically what you're looking for is a balanced model that has solid performance on both data sets. One way you can improve the performance of a model is by optimizing features. So for a model that underfits, you can add features or more advanced feature engineering techniques. So in text modeling, you might increase the number of n-grams. Okay. Or if you have a model that is overfitting, you may use fewer features, use some sort of regularization technique that will penalize the model for the use of beta or the use of a number of features, or do something to reduce the model complexity. Like, let's say, for example, you have a neural network and you add dropout layers. Hyperparameter optimization is choosing a set of optimal hyperparameters for a learning algorithm. Model performance assessment. Performance is assessed differently for regression problems and classification problems. So for classification problems, you might look at the ROC score, the F1 score, categorical log loss. For regression, you might look at root mean squared error. And generally speaking, root mean squared error is very simple to understand. It's just a way of understanding how concentrated the data is around the line of best fit. A confusion matrix is a table that is often used to describe the performance of a classification model on a set of test data. So typically you'll have the classes on the left side, and you'll have a true positive, false negative, false positive, and true negative. And what you're trying to do is to use this confusion matrix to understand the performance of your model. But first, let's talk about what these different metrics mean. So in the case we have a binary class, you have a positive event and a negative event, okay? So a positive event is an observation in which something actually occurred. Like, for example, someone's actually pregnant. A negative event is something where the observation is false or the person is not pregnant. A true positive is an observation is positive and is predicted to be positive. A false negative is an observation is actually positive, but it's predicted to be negative. A true negative is when you have an observation that is negative and is actually predicted to be negative. A false positive is an observation is negative, but is predicted to be positive. Accuracy is something you should also know. Memorize this. It's the true positives plus the true negatives divided by all the true positives plus the true negatives plus the false positive plus false negatives. Precision, recall, F1, specificity. Precision just says that out of all the positive classes we have predicted correctly, how many are actually positive? The F1 score is nothing more than a harmonic mean, and it's used to measure recall and precision. So it's the harmonic mean of recall and precision. Recall is the sum of the true positives divided by the sum of the true positives plus false negatives. So what you're saying here is out of all the positive cases, how much we predicted correctly, or how many did you actually predict correctly? Recall should be as high as positive. For specificity, it's just the true negative rate. So you take the number of true negatives divided by the number of true negatives plus false positives. AUC and ROC. So the AUC-ROC curve is a performance measurement for classification problems at various thresholds. AUC measures separability, so it tells you how much a model is actually capable of distinguishing between classes. ROC is the probability curve. The higher the AUC, the better the model is at predicting a particular class. So for example, the higher the AUC, the better the model is at distinguishing between patients that are pregnant and not pregnant, or spam and not spam. And we're going to talk about regression in just one moment. Now we're going to discuss classification modeling. Now we're going to discuss AWS SageMaker. SageMaker is Amazon Web Services machine learning interface, and it's very useful for designing a number of models using the AWS ecosystem. What we're going to do is look at the linear learner model, and we're also going to look at XGBoost, and we're going to build models using SageMaker as well as deploy them.